10.7. Why machines? A large stone rests in the middle of the front yard of your newly built house. Removing the stone will allow you to establish a beautiful level lawn. How will you remove it? You cannot simply lift such a large, sunken stone, even if you have several helpers. You may consider using dynamite to shatter the stone, but detonating explosives in a residential area is prohibited. You might think of hiring a crane to remove the rock, but that operation would be very expensive. You would probably decide, finally, to remove the stone by using tools you already have or can borrow. To pull the rock out with a lawn tractor, you would first dig around it with a shovel and put a chain around it. On the side of the rock nearest the tractor, you could place boards to form a ramp under the stone to make it slide more easily from its bed. Opposite the ramp, neighbors with pry bars could loosen the rock as the tractor pulls. This strategy would probably remove the stone from its hole in your lawn. In this illustration, several machines have been mentioned. Complex machines such as the crane and the tractor seem indispensable in modern life. However, simple machines like the shovel, ramp, and pry bars are not obsolete. Why are these called machines? A machine is a device that changes the magnitude or direction, or both, of an applied force. The force may be provided by a human or by a non-human source of energy, like an electric motor. Although machines make some tasks easier by providing an advantage that would not otherwise be available, they do not create energy. In fact, because of friction, the amount of work a machine produces is less than the energy supplied to it. 10.8. Mechanical advantage. Most simple machines amplify the effect of an applied force. How much does a machine amplify a force? To answer this question, we must define ideal mechanical advantage, IMA. One definition of ideal mechanical advantage is the force the machine produces in the absence of friction, divided by the force that is applied to the machine. That is, IMA equals F out over F in no friction. 10.2. Mechanical work is accomplished by a force component acting parallel to a displacement. In this discussion of simple machines, we will assume that input and output forces act in the same direction as the displacement of the machine where the force is exerted, e.g., theta equals 0 degrees. We make this reasonable simplification to avoid having to resolve the forces into their components. We can then represent the mechanical work function as simply W equals FD, 10.3. Since cosine 0 degrees equals 1. For a real machine, the work done by the input force, W in, equals the work done by the output force, W out, plus the work done by friction, WF. W in equals W out plus WF. You can see that friction reduces the output work in all real machines. However, for ideal, i.e. frictionless machines, frictional work is 0, and W in equals W out, no friction, 10.4. You can rewrite equation 10.4 by substituting the definition of work from equation 10.3. W in equals F in D in, and W out equals F out D out. So, F in D in equals F out doubt, no friction. Rearranging. F out over F in equals D in over D out, no friction. 10.5. The left side of equation 10.4 is the definition of IMA. So, IMA equals D in over D out, no friction, 10.6. Only 736 newtons is needed to push the piano up the ramp, compared to about 2,450 newtons to lift the piano vertically. Using the ramp made the job much easier. However, notice that the piano traveled more than 3 meters to reach the second floor. The movers paid for their easier job by moving the piano farther. The word ideal in IMA implies that IMA is perfect and thus unrealistic. In real life, friction is always present. The actual mechanical advantage, AMA, of a machine is defined as the output force when friction is present, divided by the input force. The actual mechanical advantage is more easily measured than predicted. We generally use a machine to make a job easier, because the amount of force we either can or want to exert is less than the force needed to do the task without using the machine. Therefore, in most cases, we want the machine's IMA to be greater than 1. This means that the output force is greater than the input force, and that, to accomplish the job, we have to move the load farther using the machine than we would if we moved the load directly. We will see how this works as we study various kinds of simple machines. There are two basic classes of simple machines: inclined planes and levers. Although at first glance shovels, pulleys, and so forth do not seem to fit into either category, closer examination shows that they do. 10.9 Inclined planes. Wedges, screws, and ramps are or contain inclined planes. Ramps were discussed above. A wedge is usually two inclined planes placed base to base. For example, an axe's cutting edge is a wedge. A wedge may also be a single inclined plane, such as chisel or scalpel, that is sloped on only one side. Wedges are usually used as cutting or splitting tools. A screw is a metal shaft surrounded by a helically coiled wedge. The wedge forms an inclined surface. It is much like a curving road going up a mountain. Few cars can produce enough force or traction to drive straight up a mountain. However, the slope of a winding road is smaller than that of a straight road. Therefore, less force is needed to propel the car forward and up. Figure 10 to 12 shows the difference between the force needed to counter gravity on a straight road and the force needed on a winding road. Similarly, a screw uses a spiral inclined plane to make it easier to exert great force parallel to the shaft of the screw. With climbing road, the closer the successive loops are, the less each loop slopes, and the easier it is to move the car forward. Of course, the car must travel much farther along the road to reach the mountaintop. Similarly, for a screw, the shorter the distance is between two successive threads, the pitch, the easier it is to turn the screw. However, a screw with a small pitch must be turned more times than a screw with a large pitch. A lever is usually a rigid bar that turns around a pivot, the fulcrum. In use, an input or effort force, FE, is applied at one end of the lever, called the effort arm, LE, and the output force, the resistance or load, FR, is applied by the resistance arm, LRI. You remember from Chapter 7 that a force applied perpendicular to a line passing through a pivot point is a torque. If the effort and resistance torques acting on the same pivot point are in equilibrium according to the law of moments, see section 7.13, the lever will be stationary and FELE or FRLR. 10.7. When equation 10.7 is true, there are no net torques on the lever, and the lever just balances on the fulcrum. The ideal mechanical advantage of a lever system, then, is IMA ter LE over LR, while the actual mechanical advantage can be determined from the actual forces involved. AMA equals FR over FE. 10.8. There are three kinds of levers. In first-class levers, shown in figure 10.14, the fulcrum is between the resistance and the effort forces. Some common first-class levers are seesaws, crowbars, and scissors. The IMA of a first-class lever varies depending on the relative lengths of the effort arm and the resistance arm. Since IMA chaksh LE over LR, IMA greater than 1 if LE greater than LR, IMA equals 1 if LE equals LR, and IMA less than 1 if LE less than LR. It is generally desirable for a first-class lever IMA to be greater than 1. If the IMA were less than 1, you would have to exert more effort on the machine than it delivers to the resistance. To illustrate this, try cutting through a thick cord with a pair of scissors by placing the cord between the blades near the pivot point. Then, try cutting the same cord using the tips of the blades. You must apply much greater effort to cut the cord using the tips, assuming you are able to do it at all. In second-class levers, the resistance is between the fulcrum and the effort force. As you can see in figure 10-15, the effort arm in a second-class lever system is always longer than the resistance arm, so the IMA is always greater than 1. Some common second-class levers are hinged doors, wheeled tote bags, and nutcrackers. In third-class levers, the effort force is between the fulcrum and the resistance. As usual, IMA, LE over LR. But here LE is always less than LR. Therefore, the IMA is always less than 1. A third-class lever diminishes input force. What good is it then? A third-class lever moves a resistance a large distance, while the effort moves only a small distance. Brooms and tweezers are examples of common third-class levers. But the most common and important application was employed by our Creator in the appendages of every creature with a rigid endo or exoskeleton. Nearly every major skeletal joint in your body is the fulcrum of a third-class lever. There's a simple biomechanical reason for this design. Muscles develop force at the subcellular level, and this force is applied to our limbs and appendages. Even with millions of cells contracting in unison, the total effort distance a muscle can generate is fairly small. In order to attain maximum possible movement, vertebrates and arthropods were designed with third-class levers in arms, legs, and nearly every other place where a muscle is attached to a rigid support. 10.11 Wheels, pulleys, and pulley systems. A lever has one major limitation. It can move only so far while doing its job. At some point, the effort arm or the resistance arm can no longer move, either because of an obstruction or because the associated force can no longer be applied effectively. It would be ideal if the lever arm could be continually repositioned in order to keep the effort and resistance forces applied. This is exactly what wheels and pulleys do. Wheels are modified levers. The fulcrum of a wheel lever is the axle. A force applied at the edge of a steering wheel turns a load near its center. This is a second-class lever, and it makes the load easier to turn. Larger steering wheels, which have longer lever arms radii, are easier to turn than smaller wheels. For an automobile drive wheel, a force delivered by the engine near the center of the wheel turns it against the force of static friction between the wheel and the road, the resistance force. This is yet another example of a third-class lever. It enables a force moving a short distance to move a load a large distance. Larger diameter wheels move a car farther than smaller wheels for the same angular distance that the force moves. A pulley is a grooved wheel that turns on an axle. You learned how pulleys function in Chapter 8. The radius of the wheel is fixed, of course, but the radius forms both the effort arm and the resistance arm of this special lever. Effort and resistance forces are applied by rope or string that lies in the groove as it passes over the pulley. The string enters and leaves the pulley tangentially, so the forces are perpendicular to the radii of the pulley. The pulley axle at the center of the radii acts as the fulcrum. Thus, a pulley is a kind of first-class lever. If you assume an ideal string passes through the pulley, then for every meter the effort force pulls the string. The string also pulls the resistance load 1 meter. Therefore, D in equals D out, and IMA equals 1. You could have obtained this result by taking the ratio of the lengths of the effort and the resistance arms. Since they are the radii of the same circle, the IMA is 1. Pulleys can be used in one of two ways. When a pulley is attached to a rigid support, it is called a fixed pulley. The advantage of a fixed pulley is that it changes the direction of an applied force. The applied force produces tension in the string that passes undiminished through the pulley. It is often easier to pull one down on a rope, putting your weight into it, than to pull up on the load directly. Also with pulleys, you are not limited by your reach when lifting a load to a greater height. A movable pulley works differently. The pulley is directly attached to the load that exerts the resistance force. One end of the string or rope is attached to a rigid support, and a force is applied to the other end. Figure 10-21b shows a free body diagram for the pulley load system in the absence of friction. The rope is assumed to be ideal. If all forces on the system in the diagram are in equilibrium, then sigma F equals T plus T prime plus mg equals 0n. You can rewrite this expression using vertical scalar components. Since T equals T prime Ty plus Ty equals 2, Ty equals negative mgy. Ty equals negative mgy over 2. In other words, each rope carries half the weight of the load. In Figure 10-21b, the resistance force Fr is the weight of the chest. The man holds only one end of the rope, so only one of the tension forces is the effort force, T prime equals Fe. Comparing the magnitudes of the forces, you find that Fr equals 2T equals 2Fe. The ideal mechanical advantage of the movable pulley is IMA equals Fr over Fe equals 2Fe over Fe equals 2.0. You can see then that a movable pulley doubles the effort force. However, it also doubles the distance over which the force must be applied. If the man in Figure 1021a pulls the rope 1 meter, the pulley and storage chest move only 2 meters. A system of fixed and movable pulleys is called a block and tackle system. Figure 10-22a shows a block and tackle system with 2 fixed and 2 movable pulleys. The effort force equals the uniform tension in the continuous rope that runs through the ideal block and tackle system. The upper fixed pulleys change only the direction of the tensional force. The lower movable pulleys, as Figure 1022b shows, double the effort force with each pulley. Let's see how this happens. The net force on the load is the sum of its weight and the 4 tensional forces in the ropes running through the pulleys attached to the load. If these forces are in equilibrium, then sigma F equals mg plus T plus T plus T plus T equals 0n. Now, once again, the resistance force is the weight of the load, and the effort force is just the tension in the rope. Therefore, 4T equals minus mg, 4T equals IMGL, 4Fe equals Fr. The IMA is IMA equals Fr over Fe equals 4. Notice that with 4 ropes pulling up on the load, the IMA is 4. With 2 ropes pulling on the load, as for the movable pulley, the IMA is 2. And with 1 rope pulling on the load, as for the fixed pulley, the IMA is 1. This suggests that the ideal mechanical advantage of a pulley system is equal to the number of ropes supporting the load. This is true for any arrangement of pulleys. 10th point 12. Using simple machines to solve problems. In 1852, Elisha Otis solved the problem of developing a safe elevator. He worked for a company in New York City that manufactured beds in a multi-story building, a good place for an elevator. After working to develop a safe and reliable elevator for his employer, he unveiled his design for an elevator safety mechanism at the New York World's Fair. He staged a demonstration at the Crystal Palace in which he rode his elevator to dizzying height and then had an assistant cut the support cable with an axe. The watching crowd gasped and then applauded as the safety mechanism activated and the elevator platform locked into place. Otis's invention ushered in the era of accessible skyscrapers. Modern elevators depend on simple machines. In the standard traction elevator, one that is raised and lowered by cables, the cables are attached at one end to the passenger cab and at the other end to a counterweight. This system of cables runs up and over sheaves, essentially fixed pulleys, attached to an electric motor, usually through a series of gears. As the sheaves rotate, friction moves the cables. If the supporting cables or lift mechanism fails, the passenger cab normally would plummet to the bottom of the elevator shaft, with potentially fatal results. However, a modern elevator has multiple safety systems, which also depend on simple machines to prevent this from happening. Traction elevators are lifted by multiple, very strong cables, each able to support the elevator's weight on its own, in case one or even several cables break. The failure of the lift motor presents a different kind of problem. A separate cable attached to the elevator cab runs through pulleys to 2 centrifugal governors installed in the elevator shaft mechanism. Within the governor are 2 flyweights. If the lifting motor fails or the main cables somehow become detached, the descending cab causes the governor to spin fast enough to throw out the flyweights by centrifugal force until they catch the ratchets in the outer casing of the governor. The governor engages a rack and pinion pull rod that pulls on cables that engage a friction brake on the cab, which brings it to a stop. Some elevators may also use an electromagnetic induction braking system. If all else fails, a shock absorber system at the bottom of the elevator shaft cushions the elevator's impact. Each of these mechanisms has a single purpose: to preserve human life. 10.13 Mechanical efficiency. You saw earlier that an ideal simple machine conserves energy. No non-conservative forces act within an ideal simple machine. The work put into the machine equals the work output of the machine. No energy is lost. Real machines do not work this way. Friction between moving parts causes wear. Edges become dull. Axles squeak. Ropes stretch non-elastically. Parts flex and give off heat. The work output of a real machine is never equal to the work put in. It's always less. Engineers and consumers are interested in getting as much energy out of a process as possible compared to the energy available at the beginning of the process. Since energy translates into work, they compare the output work to the work or energy put into a process to determine the efficiency, N, of the process. The efficiency is most easily determined by finding the actual mechanical advantage for the process, then dividing the AMA by the IMA. ETA equals AMA over IMA x 100%, 10.9. We will consider other methods for determining efficiency in later chapters. Stationary pulley systems are nearly 100% efficient. Their efficiency decreases when the string runs through the pulleys because of the kinetic friction occurring at many points in the system. Now, consumers are very interested in the efficiency of the products they buy. Fuel efficiency in cars and furnaces, electrical efficiency in air conditioners and laptop computers, and well-designed hand tools that provide maximum force with minimum effort are all examples of product efficiency. The federal government often mandates that manufacturers prominently post energy efficiency ratings on products prior to their sale.